necessary. So we're talking about work, and work is the force acting on an object multiplied by the distance that object moves, and we might want to do that in terms of vectors. And then we were just looking at the possibility of expressing 1 joule in SI units. And what I was saying is 1 joule equals, sorry, I've written that on a slightly wonky bit of paper, equals 1 Newton meter. We know that's because work done equals force times distance. This is the unit of work, and this is force, and this is distance. So meters is fine, that's already an SI unit. Newtons, we need to work out what is 1 Newton. And the way that we're going to do that is finding an equation with newtons in it that we can take advantage of. And the most famous equation about forces is from Newton's second law, and says that force is mass times acceleration. The units, as always, have to balance on both sides of that equation. So 1 Newton equals 1 kilogram multiplied by 1 meter per second per second. And that's, you know, we can put it together, 1 kilogram meter second to the minus 2. So if 1 joule equals 1 Newton meter, that equals 1 kilogram meter second to the minus 2 multiplied by meters, and that's 1 kilogram meter squared second to the minus 2. So that's an expression for joules in SI units. There are lots of reasons why it's useful to be able to do these kind of unit conversions. One is just to remember that if, say, the distance traveled goes up, then the amount of energy is likely to go up because energy is proportional to some kind of distance squared. And the second is that it can be a useful check for a lot of maths to make sure you're getting your equations right. And there's a whole field, which I've mentioned before, called dimensional analysis, in which we look and see what we can learn from the dimensions of a certain physical property or constant. Okay, let's go back to thinking about work. So this is the kind of very trivial, I don't want to say trivial, it's the first kind of example that we might think about. A force is pushing an object, and that object moves in the direction of the force by 5 meters. And please now put in the chat your suggested answer to what is the amount of work done by the force. Good, Unit says 50. One more thing I'd like there is the units which we've just been talking about. So it's 50 joules is the amount of work done. And that's just from work is force times distance, which is 5 times 10. Thank you, Unit. So you can see this kind of calculation isn't hard to do. It's one multiplication. But it helps us turn a force into an energy, and that can help us with lots of bits of understanding engineering. So sometimes work can be negative. I guess this is a detail that we don't really get into in any important way in this module. But it's just worth being aware, if we're pushing to the right on this screen, we've got the same kind of setup as before, 10 newtons pushing to the right over a distance of 5 meters. So this pushing force is doing 50 newtons of work. But you could say that this drag force is doing 50 joules of work. You could say that this drag force is doing 25 joules of negative work. It's working against the direction of the force, and so, or direction of movement, and so it's kind of impeding the motion, and that means it's doing negative work. And we can get to a negative here because the vector calculation will allow us to include negatives, negative directions, or opposite directions within the vectors. And then you can have problems like this, where the force isn't aligned with the direction of motion. Assuming that this block is going to move sideways again, then the force of 35 newtons, some of that is pushing sideways, but some of it is pushing down as well. This force pushes down and to the right. And so what we need to do is to do a calculation there. Bring up the visualizer again. We've got a force which acts down and to the right. This angle here is 27 degrees, and the force is 35 newtons. So I hope, I know it's been a while since we were doing this module, but I hope people remember that a lot of what we do in this module is to break things up into triangles and then do trigonometry on those triangles. And one of the reasons that we do that is because everything's much easier when we work in horizontal and vertical forces than when we work in forces at all kinds of different angles. So I'm going to break this 35 Newton force into its horizontal and vertical components. And to do that, I'll do trigonometry. Sine 27 is opposite over hypotenuse, that's V over 35, which means that V equals 35 sine 27. I'll get my calculator out. Which is 15.9 newtons. And it's acting downwards because this arrow here that we started with acts down and to the right. Similarly, I can say cos 27 is going to be adjacent over hypotenuse. That's h over 35 here. H is going to be 35 times cos 27, which is 31.2 newtons. And that's going to be to the right. So what we're saying is this force that acted down and to the right can be replaced by the effect of a force acting downwards, and that's 15.9 newtons, plus the effect of a force acting to the right, and that is 31.2 newtons. So we can now go back and think about that in the context of work. The force acting downwards in this problem isn't really related to them. It isn't in the direction of motion at all. It's perpendicular to the direction of motion. It's 90 degrees to the motion, but the force acting to the right is in the same direction as the motion. And so what we always want to do to calculate work done, to calculate the energy that it needs to move something, is to find the component of the force acting in the direction of motion. And here that's F cos theta is the component of the force acting to the right multiplied by the distance. And if I just bring the visualizer back up again, F cos theta, F is 35, theta is 27 degrees. So that's this calculation here, giving us 31.2 newtons. So that's the kind of thing that we need to do with these non-aligned forces, is to find the component acting in the direction of motion. And then there's an extreme example, if there's no component acting in the direction of motion, if the force and the motion are at 90 degrees to each other, they're perpendicular, then no work is being done by that force. And that seems a bit counterintuitive because there's a force and there's some movement, but the movement is being generated entirely by something else. A force acting straight downwards can't move something sideways unless it's redirected somehow. So then you can get into much more complicated problems, and this is now somewhat like a problem that we looked at last week, or last class, which was before Christmas, where we've got some drag force and we've got some weight, and we've got a moving block on a slope, and we need to do some calculations around that to find out what the components acting in the direction of motion are here. And you can see, for example, F acts in the direction of motion. And we're told that F is 20 kilonewtons, and it's moving 40 meters. So the work done by F is going to be this 20 kilonewtons multiplied by this 40 meters. The work done by R, the drag force, is going to be this 6 kilonewtons multiplied by 40 meters. N is completely perpendicular to the slope and to the direction of motion, so it's going to do no work. And then W is the complicated one because it has a component which acts straight down into the slope and another component which acts in the direction of R. And so we need to find that by doing trigonometry, the component which acts in the direction of R, multiply that by the distance, which is still 40 meters, always 40 meters, and that'll give us the work done by the weight. I'm going to leave that calculation, the last bit of calculation there for now. Obviously, as with everything, there are worked examples associated with all of this, and you can go through any time and look at those. But I think it's maybe a good one just to take a look at directly and see what you can learn from it by having a practice go at it straight after this class. Sometimes it's not as straightforward as saying this is what the force is, because sometimes we have forces that change. So here, for example, we've got a steadily increasing force, and here we've got a force which is some kind of complicated function that perhaps we don't even know quite what it is. In these cases, the force is the area, sorry, the work done is the area underneath a force distance plot. So that's something that we'll use a few times throughout your degrees. This is related to the maths of integration, which I don't think you've covered yet, but which is just a word to be aware of. Integration will tell us the area underneath a curve, and that turns out to be extremely powerful. One of the places where we might use it is in working out how much work is done by a variable force. So just looking at this example at the bottom of the page, we've got a force which varies over distance traveled. It increases linearly from 0 to 10 centimeters, which I'll convert to 0.1 meters. And that's 10 newtons there. This is taken from the question. It remains constant for another 10 centimeters, I think, and then it decreases again to 0, again linearly, so in a straight line like that. Increases linearly from 0 to 10 newtons for the first 10 centimeters, stays constant for 10 centimeters, decreases linearly to 0 over 10 centimeters. So that's what I've drawn here. And then we know that the total work done is the energy, is the area underneath that graph. So we can write down an equation for that, work done equals the area of this triangle, and the area of a triangle is a half times the base times the height, plus the area of the middle rectangle, which is the base times the height, plus the area of this triangle, a half times the base times the height. And when we put all of that together, this is 0.5 plus 1 plus 0.5, which is 2 joules. So that's a kind of simple example where I'm measuring a force that's acting, and that force is changing, but I'm able to convert it into a total amount of energy spent over the whole motion. And we're going to talk a lot about energy, first of all here and then later when we cover thermodynamics. But to give you a kind of look ahead, one of the things we're going to be discussing is that energy cannot be created or destroyed. It's always conserved. So if you know how much energy you need to put into something, it tells you things about how much, what kind of batteries you might need, or equivalently, how much energy you might be able to get out of this if it's a system that's doing something, creating energy or converting energy usefully. Then these kinds of calculations will tell you what the useful output is going to be. Okay. So one of the places where we know that forces change is in springs. And we know that because we've already worked through Hooke's law for springs, which says that the force is some constant of proportionality times the extension of the spring, the change in length of the spring. And that means as the spring extends, the force gets higher, and as the spring contracts, the force gets lower. And so we need to think about these things, about work done in springs, by plotting a graph. I'm going to leave this one because it's a simpler case and move to the next slide, which has this idea of a compound spring. And we'll just work through this one for 5 minutes or so. I'm just going to give everyone about 2 minutes to read the problem and to start drawing things out and see how you get on, trying to pull out the important information from the question. So we'll start again in 3 minutes time. Okay, I'm gonna. Oh, nice. Thanks, Lewis. 3750. That sounds plausible. I can't remember what the answer is, so let's take a look and see where we get to. But yeah, do it's great when people can put answers in the chat and put suggestions in the chat. So do please keep doing that. And I think, yeah, well, let's see if you and I get to the same answer. This is what I drew out. So what's going on is the force increases from 0 to 150 newtons over the first 20 centimeters. That's 0.02 meters. Sorry, 20 millimeters. That's 0.02 meters. And then it goes from 150 to 450 newtons over the next 15 millimeters, 0.015 meters. So I can draw that on my graph of force as a function of distance. It's a straight line from 0 to 150. You can be okay if you use millimeters instead of meters, but you need to do the conversion somewhere. So maybe you'll end up being a factor of 1,000 out. But let's have a look and see. It goes from 0 to 150 over the first 20 millimeters, and then from 150 to 450 over the next 15 millimeters. So my graph looks something like this. Not quite perfectly drawn. But what I'm going to do, because there's a change in slope after 20 millimeters, this compound spring is getting stiffer halfway, or not quite half, just after halfway through the motion. That means it's not immediately obvious how I'm going to calculate the area under this graph. But if I break things up into triangles and rectangles, it gets a lot easier. So I guess I can do some color coding. I love a bit of color coding when I'm marking up graphs. We've got a red area, a blue area. I guess I could even do different styles of hatching, but I'm not quite that good with my colored pens. So the red area, which we'll call A1, is a half. It's a triangle, so it's a half the base times the height. Half times 0.02 times 150. Which is 1.5 joules. A2, I was going to color code this, so I will. A2 is, this is a rectangle, a square, so 0.015, that's the base, multiplied by 150. Which is 2.25 joules. And then A3 is a half times the base times the height. A half times 0.015 times 300. Which is also 2.25 joules. So the total energy is 1.5 plus 2.25 plus 2.25, which equals, that's 4.5 plus 1.5 is 6 joules. So you can see it's this is quite an interesting one, I think. First of all, Lewis, I'm guessing what you might have done is had this number and this number, but not the rectangle here as well, which is, you know, incredibly easy to do, and certainly would be my sort of first thing that I'd end up doing with this example, if I didn't remember that it's always good to draw the graph. And so I guess a real sort of take home and learning lesson there is it's really useful to draw graphs in engineering. Pretty much any time you can, you should, I think, is a kind of basic rule there, because it's hard to visualize a lot of these things unless you're putting things down on paper. You can't, or at least I can't, juggle it all in my brain at once, but as long as I've got some of it on the page, it becomes more understandable. And so what I think is tricky here is remembering that this second phase, from 150 to 450 newtons, there's kind of there's an increase of 300 newtons, but it's from a base that's above zero. So there's work being done right from the start in this case, because we have to push against that 150 newton force. So that's the kind of thing that we can understand by thinking about work as the area underneath the graph. And I think that's kind of a nice question to practice. So what we're going to do next is to think about energy. And so work is one specific kind of energy, and it's the energy associated with a force or with forces. But there are lots of other kinds of energy. I'm sure you know about things like gravitational potential energy, kinetic energy of motion, and then there are slightly complicated forms of energy. Things like friction and breaking things take energy, and so we might even want to understand those. Just a couple of practical examples as well of places where understanding this work done is really important. When you have an earthquake, obviously the amount of energy in earthquakes is huge, but you can calculate the energy that you expect, because you know the stress in the plates. You can calculate that by, measure that directly to find out what the stress is in the plates. You can convert that into a force, and you can see how far things moved, and then that will tell you the energy that is dissipated in an earthquake. So that's a very practical example that some people have done in this science paper from 1998, calculating work. And then this is another kind of practical example about climbing ropes, which are stretchy, which can feel a bit disconcerting if you're hanging off one of them and you bounce up and down. But the reason that they're stretchy is because we're having a change of energy here. In particular, if you fall, first of all, you have gravitational potential energy, and then that gets converted into kinetic energy. And that is, you're starting to move fast, you're falling. And then the kinetic energy is released as the rope becomes tight. And so the distance that the rope gets tight over is a kind of way of dissipating energy. If you think of falling and immediately stopping, you get a large transfer of energy into you very quickly. Whereas if you think of falling and bouncing a bit, you get much less energy transferred into you and over time. So you can do some calculations around this based on the equation of work that we started with today. And you can find that the force that's going to act on you is the total amount of work that has to be done divided by the distance you travel. So if you want the force to be small for a fixed amount of work, you want the distance to be big. So you want a very stretchy rope that doesn't stop you within a couple of millimeters, but stops you over maybe half a meter or something like that. And then you won't have that jarring force that's going to cause damage. So although these things we've been doing in this lecture have seemed sometimes to all rely on this one simple equation, they can have quite far-reaching consequences. So the lecture finishes with a summary slide, which everyone will be able to see. This is all on Moodle. I know we're moving over to Aula, but because of the cyber attack, I just want to make sure that all the information is available. And now that Moodle's back, it seems a good idea to put it on Moodle, and we'll migrate to Aula more gradually than we were going to. So there you go. That is the lecture on work. Does anyone at this stage have kind of questions or observations or things that they want to flag up? Okay, I mean, do feel free to put things in the chat anytime. Thanks, Philippa. You know, I keep checking it. So if something's not making sense, or if something's worth going back and revisiting, just let me know. But I think what I want to do, I'm going to kind of press on because we're down to an hour this week. So what I want to do is go straight on to this idea of energy and power, which all links together, as I've been saying, with the concept of work. So this is one of those things that I find interesting, and it's that the cost of light has become much lower in my lifetime, and even in your lifetimes. Edison's first light bulb was an entire research project to build it, but even in 1990, the energy costs associated with a tungsten filament light bulb would have been perhaps £150 a year. These slides are a bit old now. I'm saying £18 a year for LED bulbs, but I think it's perhaps even lower than that. And so there's this interesting thing where suddenly I'm using numbers in watts. W is WATT is watt, and it's the unit of power. And these things that we're talking about in engineering classes, watts and joules and the like, you know, they're the same kinds of things that are written on the boxes of light bulbs. They're actually very practical quantities that we find ourselves wondering about a lot. And, you know, if you want to understand the efficiency of the place you live, you want to be thinking about watts and joules, just like in these engineering lectures. So that's a kind of starting point for things. This is where we've just been thinking about work being force times distance. A couple of examples. Let me just see if I can pull up this video. Sorry, I'm just getting it now. No, frustratingly, it's on my internet pages, which are not available at the moment because of the cyber attack. I'm just going to check one more place for it. Okay, we'll come back to that some other time. What I was going to show you is a video that I think I might have showed in our very first lecture of a sledge going down a sledging track, and it's some work that I did because we were working with UK Sport trying to make the British Winter Olympic team faster, effectively. So you can imagine it's a competitive sport, so people go pretty fast, sort of 70, 80, 90 kilometers an hour, head first on a sledge. and they came to us to say, can we try and understand the engineering of this to improve things? And so then this is a paper that my PhD student, Alexandra Seymour Pierce, worked on, which is looking at understanding that problem, sledging faster from the point of view of engineering. And what I want to highlight here, the reason that I'm kind of putting this into a talk about energy is because one of the first things that we were interested in this paper is how much of the energy here goes into the ice. If you want to make something better, very often what you want to do is find all the places that energy is being dissipated and then try and stop that energy being dissipated. So here we worked out that ice drag, so kind of friction, is up to half of all of the wasted energy. And if we didn't waste any energy, we'd have a lot more kinetic energy and we'd be going a lot faster. And that's really the calculation we were doing. So you can start to put some numbers in there. You start with some energy from an initial movement, and you've got some gravitational energy because you start at the top of a hill, and that either gets converted into kinetic energy or it gets dissipated. It gets lost as heat usually. When we lose energy, it's almost always as heat, just warming up the air ever so slightly. So we say, okay, we can rearrange that equation and we can put in some numbers, and eventually we can work out how much energy must be dissipated. So everything that I'm showing there on that slide is kind of the same things that we're doing in class today, and we were doing that for a very practical purpose of trying to win medals for the British Winter Olympic team. So just to, we're going to end up being a bit circular. We just talked about work and said it's a form of energy. Energy is defined as the ability of a system to perform work. Sometimes we're going to end up with these kind of tautological definitions, I'm afraid. But it gets easier once we look at forms of energy. So we know something about what kinetic energy is. It's associated with a moving object. We know things about potential energy. So if I lift something up high, it's got a lot of gravitational potential energy. We did some examples earlier with a spring and the energy stored in a spring. Well, that's a form of elastic energy. And if you remember that Hooke's law for springs is kind of similar to stress-strain relationships, then as well as springs having elastic energy, anything that's strained, that's either compressed or stretched, holds some elastic energy. And then, you know, we can keep on going. Chemical energy, electrical energy, nuclear energy. So the E in E equals mc squared, Einstein's equation, is energy stored in matter. And then heat is a form of energy. And one of the things that we'll keep thinking about is that when you lose energy, you tend to lose it as heat. So we've already talked about joules being kilograms square meters per second squared. Sometimes it's kind of useful to have in mind, is that a big number? You know, and 1 joule isn't really a big number. The energy required to lift a tomato 1 meter, or the energy being used by a bike light in 1 second, or the energy required to heat 1 gram of air by 1 degree. So those are not activities that we would associate with hugely energetic properties. You know, they're not like the earthquake that we talked about in the last slides. And then this is kind of linked again, and we'll come back and talk more directly about thermodynamics. But there's this really important first law of thermodynamics, that energy cannot be created or destroyed. And so whenever we're thinking about energy, we need to be thinking about it being transferred from one form to another. And that's why we can write equations, because the amount of energy that goes into something is going to be equal to the amount of energy that comes out of something, and that equals allows us to write an equation. The second law of thermodynamics is about something called entropy, and we won't go into that in great detail, but it sort of means that the amount of disorder in something, the amount of energy which is unavailable to do work, is increasing over time. So it's to do with order and disorder in a vaguely hand-wavy way. And then you can't go below absolute zero, and that's another, the third law of thermodynamics. We'll come back and look again at these, but the important one for now is that energy cannot be created or destroyed. Kinetic energy. The equation for kinetic energy is that it equals 1/2 times mass times velocity squared. And so you can put this kind of calculation together where you have something that is accelerated and you want to know how much energy is transferred into it. Well, you know how much energy is going to be transferred by a certain force, because it's that can be a work done calculation, and then you can use that to say, well, if all of that becomes kinetic energy, we can tell how fast something is going to end up going. We can calculate V. So that's what we would be doing here. Again, the worked examples are all available. I'm going to keep going to try and get to the major content of these slides done. Gravitational energy, again, we have an equation for the energy associated with lifting something up. If I lift up my pen, then the energy I add is the mass times gravitational acceleration times the height that I lift the pen. And so an example of an easy calculation that we can do, or a calculation we might do a lot of, is if you drop something from a certain height, how fast is it going by the time it falls 1 meter or 10 meters? And we can do that by considering the conversion from gravitational energy into kinetic energy. We talked a bit about the energy stored in springs, and if you look in detail at the kinds of graphs that we were drawing in the last lecture, those graphs had a triangle, and we put some numbers on that triangle in each of the calculations that we did, and then we found out the area underneath the triangle. If instead of using numbers, we stick with algebra, we can draw a graph. Let me just do it very quickly. I think it might be helpful, and then we can start to bring things to a close. If I have a graph which is force against distance, and we know that when you push on a spring, you get a straight line graph, the force increases with distance, then let's say that distance traveled is S1. Then we know from Hooke's law that F equals K delta X, where K is some stiffness and delta X is distance compressed. So this number here is the force, the force is K multiplied by the distance, and the distance is S1. And so this shaded area is 1/2 times the base times the height, which equals 1/2 times S1 times KS1, which equals 1/2 KS1 squared. So this is the energy stored in a spring with stiffness K and compression distance S1. Sorry, that wording's a little bit clunky. Perhaps I could have said with stiffness K and compressed by a distance S1. But that was just to show you that this slide here relates directly back to the kinds of things we were doing, thinking about the work that's gone into a spring. Well, we know that energy is always conserved, so the work required to compress a spring must be equal to the energy stored in that spring. Okay, I think what I want to finish on, and maybe an example for people to take away and think about, and then we'll start with this at the beginning of next time, is this question about estimating energy. So we've got here 10 different things which we can understand as being a process involving energy. So for example, a car on a motorway will have some kinetic energy, and a AA battery contains some chemical energy. And what I want people to do, and maybe just if you can take 10 minutes after this lecture and go in, have a go at it, is to think about ranking these in order. So which one has the most energy, second most, third most, all the way down to the least energy. And you can do some of that using these equations here. You might have a good sense of, for example, how fast Usain Bolt runs and how much Usain Bolt weighs, and then you could calculate Usain Bolt's kinetic energy. And then some of them we're just going to have to make a gut feeling about, you know, is that a big number? Is that a small number? Is there any way we can get an intuition or start to put some bounds on that number? So I'm going to stop the recording there, and